Hi, I'm Summer,
Hi, I'm Tim.
and we're going to be going over Thebault's theorem problem number 1. So today we're actually going over the problem which says, given any parallelogram, erect a square on each of its 4 sides. The resulting shape of connecting the center of all 4 squares is a square. So we start off with a parallelogram, and then we have 4 squares on each side of it, and draw its centers, and then connect it to form a shape, which we are going to prove later is a square. So
Parallelogram. So, what do we know about parallelogram? A parallelogram is a quadrilateral with opposite sides parallel. Quadrilateral means any 4 straight-sided connected shape, and parallel means lines of sides that continuously have the same space between them and will never intersect.
So we're going to start off with the basic shape of parallelograms, which is both parallel and a quadrilateral.
The next one is just a 4-sided shape, but it is not parallel.
And then this one, even though opposite sides are parallel, the definition of a parallelogram states that it has to be quadrilateral, which this has more than 4 sides, so therefore it is neither.
And this is a typical example of a parallelogram.
A trapezoid is not a parallelogram because both opposite sides are not congruent, so therefore it is only a quadrilateral because it does have 4 sides.
This is obviously an oval, so it's neither a quadrilateral or parallel.
And this is a basic rectangle, which is both a parallelogram and a quadrilateral.
And this is neither a 4-sided shape, so it's not quadrilateral, and it's neither parallel. What do we know? Squares. A square is a quadrilateral with 4 congruent side lanes and 4 congruent interior angles. Congruent means equal measures of length or size. Interior angles means angle within and bounded be the respective figure.
So here we have a square, and we're showing on all sides that the measure is the same, so therefore all sides are congruent. And this is an example of an interior angle.
Center. The center of a symmetric object is where the diagonals of the shape intersect and will be unchanged by symmetric movement. Symmetric. It means having symmetry, made up of exactly similar posts on either side of an axis. An axis is an imaginary line about which a shape rotates, and symmetric movement means when the same kind of movement happens on both sides of the axis. And the following 2 definitions are very self-explanatory, but diagonal means a line that goes from one corner of a shape to its equally opposing corner. And intersect means where lines of sides cross or lie on each other. This point or points is called intersection.
Alright, so our first proof is going to be showing that extends from our definitions is that a square has perpendicularly bisecting diagonals. So first, to prove that, we're going to draw the diagonals of square ABCD. So here's our square, and the diagonal will be AC and BD. A square is a special kind of rectangle, as we mentioned earlier when talking about parallelograms, that a rectangle was a parallelogram, so therefore a square is also a parallelogram. And we also said that a square has all equal congruent sides, so therefore AB equals BC, which equals CD, which equals AD. And a line that cuts through 2 or more parallel lines is called a transversal. So AC is a transversal of both the parallel lines AD and BC, as well as AB and CD. Similarly, BD is also a transversal of both sets of parallel lines. Therefore, angle ABE, so this angle right here, equals angle CDE. So this angle right here, because of alternate interior angles, looks very similar to this picture up here. Similarly, but flipped, angle BAE and angle DCE are also congruent by alternate interior angles. Thus, triangle ABE and triangle CDE are congruent by angle side angle criteria.
Okay, going further, as we prove, side line BE is equal to line DE, as well as line BC is equal to line DCC. And by the reflexive property, we have EC equals EC. Therefore, triangles BEC and triangle DEC are congruent with each other. Thus, the angle DEC, so this angle right here, and the angle BEC, this angle here, are equal to each other. Since these 2 angles are supplementary to one another, they equal 180 degrees. With basis substitution, we can yield the equation 2 times the angle DEC equals 180 degrees. Divide 2 by both sides, and we get angle DEC is equal to 90 degrees, as well as the angle BEC is also 90 degrees. Therefore, the diagonals of a square perpendicularly bisect each other.
Right, some other useful background knowledge that'll be helpful later on. Going over SOHCAHTOA, so sine equals the opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent.
Yes. The line of law of cosines. When we know three sides of a triangle, or if we know two sides and the angle between them, then we can use this expression. So for example, if we knew the angle A and sides B and C, we can calculate and plug in the variables to get and obtain side A, lowercase a.
Alright, next we're going to go over some trig identities, specifically angle sum trig identities. These equations will be useful later when we are have an angle and a degree for another angle.
And also, with the unit circle, it's important to revisit this because we'll be using it with the proof. For example, if we have 45 degrees, an angle 45 degrees, hence pi over 4 radians, then the cosine of that would be the square root of 2 over 2, and the sine value of that would be square root of 2 over 2.
Alright, so actually getting into the proof now. From previous knowledge of us talking about how the diagonals of a square bisect each other. So if we continued this would be our full diagonal of this square. But since we only have half of it, therefore half, AE is half of what we would extend to be AC, as we proved by bisecting diagonals before.
Yes, and by using the law of cosines, we have line AE equals to 1/2 times G times the square root of 2 over 2, and that yields G times the square root of 2 over 4. And also we can do the same thing for line AH, which yields 1/2 times F times the square root of 2 over 2, or we can simplify it and we get F times the square root of 2 over 4. And also angle EAH is equal to angle A, this angle, the one within the parallelogram that we drew in the beginning, plus 90 degrees. If we plug in these equations to the following law of cosines, we have this equation, and if by basic substitution we finally yield the line EH squared is equal to 1/8 times this whole expression, G squared plus F squared minus 2GF cosine the angle of A plus 90 degrees. As angle A and C are equal to each other,
And then we could follow the same type of manner for finding angle C over here for this triangle. And so therefore, since by property of a parallelogram, opposite angles are congruent, so therefore this angle right here, angle A and angle C, the ones that we were solving or have unknown here, are congruent. And so since angle A and angle C are congruent, EH, this line, and FG are also equal. Therefore, similarly, EF and HG are also congruent by the similar process.
and that makes sense because opposite angles of a parallelogram are equal to each other.
Alright, continuing on.
Yes. So by using one of the angle sum trigonometric identities, cosine and with parentheses angle A plus 90 degrees, it forms this expression. This is a new way to rewrite it. And so if we were to plug it in from our original, we get
Let's show where we get this from. So over here we have angle A, and our 90 degrees angle is from right here, which we are going to manipulate later.
Right. Yes. So by substitution, we get 1/8 times the whole G squared plus F squared plus 2GF times sine of angle A. And it's important to note if we have the angle BAD, so this angle right here, it equals the angle LBN. So this part we just basically extended or drew a similar parallelogram.
Yes, since both sides, or since we were able to get these squares from this parallelogram, we have the same squares and we just basically rotated the parallelogram we already have and extended it over here. And then therefore extended these parallel lines to create our other angles over here.
Okay.
And so EF or angle EBF, so this is B right here, I know it's hard to see, but EBF for our triangle equals LBN plus EBL plus NBF. So this whole triangle right here is made of these three angles, which we just added together. And we know that these two angles right here, not including this orange one, are both 45 degrees, therefore 90 degrees. So both of these two angles plus this one is this equation right here. And similarly, we can do the same thing for this triangle over here.
Okay, so angle EBF, this angle right here, it equals angle LBN plus 90 degrees. And this is also equivalent to angle BAD plus 90 degrees, which also equals this angle EAH, this right here. And we'll mark this as 1. We'll come back to it later. So we have side EA is equal to side EB, and side AH is equal to side BF. Therefore, by the side angle side criteria, triangles EBF and triangles EAH are congruent to each other. Also, we can also note and say that sides EH and sides EF are equal, as well as sides EF is equal to being sides HG, and size EG is also equivalent to size FG due to law of cosines. So now we can say that this quadrilateral is a rhombus. Quadrilateral EFGH is a rhombus. In addition, we can also say that angle BEA is 90 degrees and angle BEA is equal to angle BEH plus HEA. Or with base substitution, we can substitute it in for angle BEF. And so we get angle BEA is equal to angle BEG, which is also equal to angle BEF equals angle HEF. Thus, we can say that the angle HEF is 90 degrees. And since we said that one of these angles in the rhombus are 90 degrees, we can say that by looking back and taking note of number 1 and number 2, quadrilateral EFGH is a square.
And that's it.